Hi guys, today we're having a go at one of the experiments linked to force, mass and momentum. I'm going to go, in a few minutes you see me kind of in the lab going through the experiment, but I've also uploaded a scan of the experiment from your experiment book. So if you're lucky enough to have your experiment book at home, you can just have a glance at it. It's on page 63 and 64. Um, yeah, but if you don't have a copy, I'll attach a scan of this assignment, and it'll also appear at the end of the video. Your main mission for this one is, after we get the results, I want you to calculate the initial and final velocity of the air-track rider, then calculate the acceleration, and then I want you to graph it and just do the best you can. I'll explain a little bit more at the end of the video, but for now, as I say at the start, there's a bit of shaky camera work, and somewhere along the line I might be referring to like take 2 and take 3 and take 4 and take 5. That's because there's bits I've cut out for everyone's benefit. Alright, best of luck, and I'll talk to you soon. Hi guys, I hope you're doing well. We're going to keep going on with the force, mass and momentum stuff, and today I'm just going to run through an experiment that we would be doing if we're back in school. But the only problem is it's one of those experiments where you've only got one set of equipment, so as things to miss out on go, it's not too bad, because it will be one of those times where we'd have to try and get everyone around the one set of kit, so it's pretty tricky. So I'm going to kind of get started. I might have to edit this later on because this is all kind of a new setup to me. But what we're going to be using is, if you remember the light gates from last time, so just to remind yourselves kind of how they work. So this is a light gate, and it's made of, there's a beam of light leaving here that's detected by a receptor there, and if I break it with my hand, this timer here can detect when I break it. And how it works is, when the beam of light breaks, if you just watch the timer starts. And when I remove my hand and let the beam of light re-establish, the timer stops. So what this means is, if I put a rider on it, this is called its metal bit, and I pass it through the light gate, the timer will tell me how long it takes for that to pass through, because it starts the timer as soon as this first part of the card goes through, and stops it when the second one goes through. So this will tell us in milliseconds, sorry, hundredths of seconds. This would be 7.37 seconds. This will tell us how long it took for this card to pass through. And I've hooked up two of these. One gate one is here, so that's the initial velocity, which we're going to look at this in a moment, and the second one over here for the V. So, the crux of it is, this will tell us how fast the rider is moving at this point, and how fast it's moving at that point. So beyond that, if that was all we had, that's not really that useful. But if I measure the distance between the two light gates, then we have enough information to calculate the acceleration. So we've got the initial velocity, the final velocity, the distance in between the two. We can figure out the acceleration. Okay guys, I'm just interrupting myself for a moment to just show you how we do these calculations and how we figure out the velocity and then the acceleration. So first off, this is just a quick sketch of our experimental setup. This is meant to be the rider that goes along the air-track blower, which I haven't drawn in. Let's just say that's the air-track blower. The only purpose of the air-track blower is to reduce friction, so to make it clearer that whatever force we apply results in acceleration, just to make it easier to get this moving. So we have the rider and the air-track blower. I haven't drawn on the weights, but I've got the card on the top, and we measured the length and it came out at 0.08 meters. It's going to pass through the light gate, breaking the beam, which sets off the timer, and then when the beam is re-established after the card passes, the timer stops. So really what we're doing here is we're just doing the simplest speed calculation ever. I'll come back to the difference between speed and velocity in a moment. Speed is just distance over time. How far somebody travels versus how long it takes to do that. Whether you're cycling at 30 kilometers an hour, or walking at 4 kilometers an hour, whatever, or throwing a ball at a certain amount of meters per second, it's just distance divided by time. And in our case, the distance is the card length. How the distance is the length of the card, and the time is the time it took to pass through the light gate, which we get from the timer. And if I was being a little bit more strict, I'd say really it's not speed we're looking for, it's velocity, which is displacement over time. Which again, the card length divided by the time to pass the light gates. Okay, next we'll look at how we calculate the acceleration. I'll just make sure you can see that if you're trying to pause the video later on. Back in a second. So you might be able to sense that SUVAT is going to make its reappearance, and you're absolutely right, the velocity and acceleration calculations. So I'm going to use our first result as an example. So in our first result, it took 0.17 seconds for the card to pass the first light gate, so that's T1, and T2 the second time. At the second gate it took less time, it was 0.12 seconds to pass through. So to calculate the initial and final velocities, so just move these up a little bit here. Well, first off I'm going to start off with just the most simple one. So if looking for speed or velocity, it's just distance traveled over time, or in the case of velocity, displacement over time. So it's just speed is equal to distance over time. Velocity, just like I explained before, is displacement over time. So let's put them in for these numbers. We have the time, we have the length of the card. So for the first one, its initial velocity was 0.08 meters divided by 0.17 seconds for a initial velocity of 0.47 meters per second. And the second time round, it was moving faster when it hit the second light gate. It only took 0.12 seconds for it to pass through the light gate. So the final velocity was, again, displacement over time, 0.08 meters divided by 0.12 seconds, 0.67 meters per second. So we just calculated the initial and final velocities. Let's go back to our SUVAT. I'll clear this up a little bit. So we have initial was 0.47 meters per second. We have our V, which was 0.67 meters per second. And if you remember, I measured the distance between the light gates and I set it up to be 1 meter. So the displacement between the two is 1 meter. Now we don't know the time it took to traverse the 2 points, and we don't know the acceleration, but that's really what we're looking for, is the acceleration. So let's have a look at our SUVAT equations, which I have prepared earlier. So we have V equals U plus AT. So let's think about that one. It's got A, which is what we're looking for. We don't know what T is, so that one is no good to us. We have A equals V minus U over T. Again, we don't know T, so that's still no good to us. S is equal to UT plus half AT squared. Still got T involved, no good. But let's look at this last one. V squared is equal to U squared plus 2AS. Okay, well A is what we're looking for, and we know everything else. We know V, we know U, and we know S. This is our winner. So let's go with that. So let's go with V squared is equal to U squared plus 2AS. And now it's just a matter of rearranging. We're looking for acceleration on its own. So I'll keep the A on this side for a few minutes. I will flip it at the end. So if we want to keep the A on one side, let's bring the U squared across. So it's V squared minus U squared. Or alternatively, you could say you subtract U squared from both sides, whichever you're showing algebra. And now we want to get rid of the 2 and the S, which are multiplied by the A. So we're going to divide the whole shebang by 2S. And now we've got A on its own. So the acceleration is equal to V squared minus U squared over 2S. And just because I'm a bit more comfortable with it, I'm going to put the A on that side. A is equal to V squared minus U squared over 2S. So that's how we're going to calculate the acceleration. Okay, so now that we know how to calculate the acceleration, we're going to go back and look at the footage from the lab earlier and put it to use. A quick note, as I was recording this stuff earlier on, I was under a bit of time pressure to get ready for the next class. And I think I made a couple of mistakes. One was, when I was talking about the little, I'm going to use the word mass and weight interchangeably here, but we talk about the little clunks of metal, right? Their mass is just their mass in grams, how much matter they have. Their weight is how much gravity pulls them with newtons. So sometimes, I can't remember, I think I get mixed up, I think I sometimes said this as a mass of 0.1 newtons, which is a really bad mistake, because remember, its mass would be 100 grams, its weight would be 0.1 newtons. So just to clear that before we go back to that. Yep, that's it. See you in a bit. What we're going to do today is we're going to see if the acceleration that we get as a result of a force is directly proportional to the force. The force we're going to use is gravity. So what I've done here is I've got this rider, and I sticky taped on 1, 2, 3, 4, 5 of these masses on each side. Each one has a mass of 0.1 newtons. And I'm also going to connect it via string to this other 0.1 newton hook. And what I'm going to slowly do is I'm going to transfer mass from here onto here. Now the overall mass of the system, if you think of this as just being essentially attached to here, is the same. When I transfer mass from there onto here, it's still in the system, it still needs to be accelerated. All we're doing is when I add more mass onto this side, on the string, when we drop it, it's going to cause it to have more force applied. So it'll be applying to the same mass, even though I've transferred the masses onto this hook, it's still the same system. So don't think of it as this mass being what drags down the whole shebang. Think gravity as the force, and we're controlling how much force is applied by controlling how much of the mass is over here. So we're just redistributing. So one more time. The overall system is going to have the same mass, I'm just going to be transferring them from the rider part onto the hook part. And we're going to see how that affects the acceleration. So, we need a couple of pieces of information. We need to know the length of the card, and we need to know the distance between the gates. Now, I've already measured a couple of these. The distance between the gates, I've deliberately chosen to be 1 meter to make life easy, and the card length is 11 centimeters, but we don't like centimeters, we like meters. That's 0.11 meters. Oh, no, I tell a lie. It's not 11. It's 7, isn't it? Let's just double check. Sorry guys, the editing process here is, as you can see, dodgy. So in fact, it's 8 centimeters. I beg your pardon for the mistake there. So the card length here is 0.08 meters, because that's what 8 centimeters are meters. Okay, so we have pretty much everything we need to get going. So I'm going to pause the video for a moment while I hook things up. It's going to get a bit noisy because I'm using the air track blower, but I'll just run it a couple of times and, you know, I'll come back. Okay, turns out the string had just gotten hooked on a little cog. So that was with 0.1 newtons. And I'm going to record the two values of U and V and use them to calculate the acceleration. And then later on we're going to see how that's affected as I transfer the masses across. So it was all working, just the thread got a bit tangled. Okay guys, so what I'm doing here is I'm just going to record the times as we go. And now what I'm going to do, and hope this is stretch, I'm just going to take this mass off here. And I'm going to transfer it onto our hook. So the whole system still has the same mass, but now there'll be more force accelerated. And I'm going to record the initial and final velocities this time. And eventually it'll give us a fairly clear picture of the acceleration. So let's keep cracking on. Forgot to end. Okay, here you go. 0.2 newtons, take 5. I think I have it solved. So I'm going to turn on the power. Hey, here we go. Let's see. Okay, so we've got a bit of an increase in velocity of both U and V there. So I'm going to put those into our spreadsheet. I'm going to do the rest and I'm going to send you the results. This is 0.3 newtons. .4 newtons, take 2. The cart is actually slowly shaking itself apart as it gets faster and faster. Every time it hits, it's getting better. I had to cut it short there because shortly afterwards the whole thing almost literally fell apart. So we have the first 5 results. Now I've already calculated the acceleration for, sorry, the velocity and initial velocity and final velocity for the first one. I want you to do the same for the rest. So what I want for you guys is to calculate for each force, the initial velocity, the final velocity, and then I wanted to calculate the acceleration. And the final thing, the big beast of a task for this week is I'd like you to graph it. Give a shot at graphing it. So don't worry if it doesn't look perfect. Just do your best. Try and label your axes, include your units, keep it neat, do the best you can. Send me what you have. We'll definitely be practicing graphing in school. But this just as a little kind of precursor. So what I want to do one more time, your main mission for this time, I'm going to put on in a moment the results, which just have the time at each light gate. And from there, I want you to figure out the velocity, initial velocity and final velocity for each reading, and also the acceleration for each one. So you have to do, I think it's like the calculations for the 4 sets of results. And remember, the length of the card was always 0.08 meters. That's constant. And the distance between them was always 1 meter. Now guys, very involved video today, so I hope you stayed with it. As always, any questions, any problems, don't hesitate to give me a bell, okay? And do your best with the calculations, especially with the graph, and send me on what you have. All right, I'll talk to you soon.